Okay. So let me start by going through the syllabus, explaining what is going to be planned for the upcoming semester. So first of all, my contact details are put right here, so you can reach me at any time with any questions. We probably gonna have a reader. It's potentially, I really hope so. If we don't have a reader, we probably will have like cross check of assignments, meaning that you probably will be checking other people's assignment, like each other's assignments, like randomly matched people's assignments. But we will see if probably it's not necessary. We're gonna have two hours of lecture and 1 hour of discussion, which is gonna be most probably is gonna be just a continuation of the lecture in a way. Discussions are gonna be focusing on the examples and on answering your questions. I'll try not to cover kind of new topics during the discussion section, so that you don't really have any disadvantage if you don't if you cannot make it to a particular discussion. Just watching the coming to the lectures should be enough. Our main course website is B Courses. I also have a website if you still haven't gotten into the class. I will duplicate all of the material there. Regarding the prerequisites. Oh, so let me see if there's any question up to this point. Everything was quite simple so far, right? So regarding the prerequisites, I really hope that you have the background about like mathematics. Linear algebra would be particularly useful here. Like knowing how to multiply matrices and vectors is definitely a must. We also gonna have some material that was that has been covered in IOR 162 and CS 170. Basically, it's the principles of linear programming and the principles of theoretical computer science, meaning the reducibility and the theory of complexity of computational programs. This matters will like I'm not planning to cover this matters specifically, like in depth. You will not need them. We're not going to be solving very complex linear programming problems, but for the sake of completeness of your understanding of what is going on, it would be beneficial if you have at least some understanding about like how what exactly is linear programming and how people approach it. For your convenience, I also posted some additional materials on the website, on both websites. So feel free to refer to that. There are literally several pages for you to read, just in case. Experience with the programming language is also preferred. In particular, I will be giving you examples with Python. At some point, we even have a lecture that is covering a Python-based tool for integer programming. So if you have that experience, it's a big plus. If you don't have, it would be really cool if you could just like take a look at what the programming language like a script programming language looks like. Okay, so we're gonna be following closely the textbook, the Wolsey textbook. Later in the course schedule, I'm referring to this textbook. So these are the numbers of the sections in this textbook. You can always continue reading after the lecture or preparing for the lecture by reading the sections. Also, as additional materials, since some of the topics will be about like convex optimization or linear programming. So there are also a couple of books listed here, and there is also a couple of resources on a separate software called Ample. I do not plan to use this software throughout the course, but for your information, the rest of the courses on our department are normally using this software, like this Ample software. So if you would like to get familiar with that, you can read it on your own and ask me questions if you have any. I can help you with that too. Any questions regarding the prerequisites and the materials? No questions? Okay. So the course schedule, it's quite straightforward. We're gonna have 6 homework assignments. At least this is what the plan is. Here are the due weeks of each of the homework assignment. You can see that homework 3 is planned to be released before the due date of the homework 2. So at some point you are going to have several homework assignments. To make sure that you have no debt, I my suggestion would be to be done and submit the homework before the new homework gets released. But if you are late for that, you still have 1 week to complete it. The homeworks are going to be due the moment before the lecture. So before the 2 p.m. on Thursday, you need to submit your homework. The homework is being submitted through B courses, and also is being downloaded on B courses at the files folder. Right. So this is regarding the assignments. There will be a midterm and there will be a final. Both of them are planned to be in class unless anything unexpected happens. There will be a policy where, well, basically, you will be allowed to take one of the problems home if you were not able to solve it. At least this is what the plan is. We'll see if we need this at all. So if just in case you have solved all of the exam, but one problem is still kind of, you are thinking about it, you'll be able to take it home and submit it later, just to reduce the pressure on you. The weighting the weighting of the homeworks midterm and the final is going to be almost equal. We put 0.4 on homeworks, 0.3 on midterm, and 0.3 on final. I strongly encourage any kind of feedback that you can give to me. You can talk directly, or if you feel like you would like to submit more anonymous feedback, you're welcome to use the form. You can also use it without any specific feedback, just to help me understand what's the basis like, if it's too easy or too hard for you. But I will remind about that later. Yeah, I guess this is it regarding the syllabus and the plan. Any questions so far? Sounds good. Okay. So let's turn to the matter of our subject. Yeah. So one thing that I did not mention is that there is bCourses discussions functionality available to you. If you prefer any other kind of ways of communication within the class, like inside the class with your peers, you are very welcome to organize it for yourself, or I can do that for you if you would like me to. So what is an optimization problem, right? In general, we are if we are talking about optimization, we are most probably talking about maximizing or minimizing an objective function, which is called f which is denoted with f0 here, of some vector argument x over a domain capital X. You can think about it as, I mean, we're going to be normally thinking about the domain X as a subset of Rn. And it's gonna possess some properties. Usually, X is given to us through a system of inequalities or some verbal description. For example, when we write down an optimization problem in this form, we imply that the set X is given to us through a set of inequalities. So it's a set of X's, so that all of the inequalities of X are satisfied. So, but basically, this this notation is equivalent to this notation if we substitute X of this form. We are referring to the vector X as the decision variables or the unknowns, x1 through xn. The particular components of this vector are the particular decision variables. F0 is the objective function, or which is given to us through the data. So this is part of the information that defines the problem, the objective function. The functional the function of through which the inequalities are given to us, fi's, are the constraint functions, which are also part of the data, meaning that those are given to us as well. We don't have to find them. And the inequalities themselves are called constraints. In the end, we can see that there are two important like numbers that are present in here. First is the n, the number of variables, and second is the m, the number of constraints. We will like these two numbers, n and m, are called the size of the problem, which are quite important if we are talking about the complexity of the problem. Just to keep that in mind. We are calling a particular vector x hat a feasible vector if it satisfies all of the inequalities, or in other words, x hat belongs to the capital X, the set capital X. X hat is said to be optimal if it's feasible, and for any like x tilde in the set big X, f0 of x hat is less than or equal than f0 of x tilde. This is in case we are talking about the minimization problem. So less than or equal is viable for minimization problem. If we're talking about maximization problem, then f0 of x hat must be greater than or equal than f0 of x tilde for any x tilde. This is the general understanding of optimization problems. What about the particular? So okay, let me motivate the whole story first. Why are optimization problems important? Generally speaking, well, by solving optimization problems, we can find an opportunity to save resources or increase profits. And if we are talking about finances, if we are talking about transport allocation, we can allocate transportations more optimally by increasing the number of lives that are saved in hospitals. Making predictions, meaning like the modern machine learning and data science, big data, all of them have optimization of problems in their core. So basically, in order to find a machine learning model, you are required to solve an optimization problem. Improving security is also possible through the methods of optimization. Generally speaking, it's a very vast matter of things, and even applications in theoretical physics, like minimization of energy, are in order. So it is kind of a very useful thing to know how to solve optimization problems. And the two examples that we can provide with would be the fitting of data, the problem of fitting of data, and portfolio optimization. In case of fitting of data, our variables would be the parameters of the model, meaning that if you have a model of I don't know, some linear phenomenon, like you probably have heard this example before, where we have the height of the parents and the height of the kids be related as a linear function, where a linear function is given to us through essentially two variables, two parameters, the angle beta and the basically the bias b. So b and beta would be the two model parameters. We have data, which are, for example, the data points on the plot, and we have some prior information, parameter limits as the constraints, and the objective would be to measure the misfit of prediction or of predictional error. Essentially, we are minimizing the average distance between the points on this plot and the points on the line that we are trying to fit. If we are talking about the portfolio optimization, the variables are amounts invested in different assets, and we have constraints such as budget or minimum return, and or like for example risk averseness would be another constraint, and the objective would be to minimize return variance or maximize the return, or any kind of money related objective you can think about. After that, I will skip to the definition and introduction of linear optimization problems. Are there any questions regarding the very basic, the very general concept of optimization and why we need it? No questions yet? Okay, so let me turn to one of the most important examples of optimization problems, which is the linear optimization. In linear optimization, our function f0 of x is given through a linear function cx, where c is a row vector, c1 through cn, and x is the column vector, right? x1 through xn. And this is the inner product between the two. So the f0 here is a linear function, just because cx is a linear function of x. The constraints are given to us with the following system of inequalities: ax less than or equal than b, and x greater than or equal than 0. If we would like to represent this in the form that we have had before, like f1 of x less than or equal than 0, and so on, fn of x less than or equal than 0, then we would have the following form: the summation over I a0 I xi less than or equal minus b. Sorry. Xi minus b 0 less than or equal than 0, and so on, summation over I a n a m I xi minus b m less than or equal than 0. So our functions f1 through fn are fm are also linear functions, just because a0i and ami are also vectors, and the scalar this is basically a scalar multiplication of vector a with a variable vector x, which is also a linear function by itself. Therefore, we are saying that linear optimization problem is a problem where the objective function and all of the constraint functions are linear functions in the variable. Just a reminder: a linear function is like we are saying that f of x is a linear function if f of x plus f of y is equal to f of x plus y, right? Just a reminder. And f of alpha f of x is equal to f of alpha x. So can we actually solve this type of problem sufficiently? The background, probably the previous courses or the additional material would tell you that yes, we have quite efficient algorithms for this, such as the interior point method and the simplex method. Another way to solve simple problems, we will talk about it, how exactly you can solve a problem if it's let's say of just two variables. But if we are talking about the general instance of a very large problem that people, for example, might stumble upon in the applications, we can actually solve this problem in quite efficiently in the polynomial time. Another thing is that this entire story about linear optimization problem was developing since the 60s, and so people have had enough time to develop a mature like field around the theoretical tools and the practical tools for solving linear optimization are very advanced by now, and we don't have to go very far in order to find a tool to solve this kind of problem. So this is I'm talking about this just to stress that linear optimization problem is actually quite a simple problem. One example of a linear programming problem is the following. So here we have the three components of the variable vector x, x1, x2, and x3. The scalar multiplication of two vectors c and x is just c1 x1 plus c2 x2 plus c3 x3, where cj's are the parameters or the data that are given to us with the problem. The system of inequalities ax less than or equal than b is rewritten for us in this form. A11 time. So basically, this part right here is the scalar multiplication of vector A1 with the vector x, and this part right here is a scalar multiplication of the vector A2 with the vector x. And the last part is the so-called non-negativity constraints. Which basically are saying to us that all of the variables that we are talking about have to be non-negative. In this problem, the aij's, bi's, and cj's are the parameters of the problem, and xj's are the variables, are called the variables. So we are like if we are given the three numbers of like the three types of parameters, we're gonna be solving like our solution would be represented with a trio of numbers xj. Any questions regarding the linear optimization? By the way, I didn't stress on it, but if you have any questions along the way, I will keep asking. But if you have any questions along the way, please feel free to interrupt me and ask it. Okay, so let's talk about now the integer linear optimization problem. Um, generally speaking, nothing restricts us to just add integer constraint of this form, for example, into the general optimization problem, where we have f zeros and f i's, but that problem is actually quite complicated, and it's not too too much different from the linear case. So we're going to be talking about integer linear optimization specifically, to stress that the functions f zeros and the function f i's, the constraint functions, are all linear in our case. The only thing that differs from the completely linear case is this set of constraints that is telling us that um, the the vector x has to have integer components, the variable vector x. Um, so how has the feasible set changed compared to a linear optimization problem is by introducing a new set of constraints, uh, saying that each component belongs to a set of uh, integer numbers. Why do we need integer variables? Uh, Generally speaking, uh, like uh, for example, logical conditions, countable objects like the number of trains or buses or machines, uh, or even modeling nonlinearity sometimes require you to introduce can be modeled through integer variables. So there could be multiple reasons for that. Do we know how to solve this type of problem efficiently? Unfortunately, after we have introduced this new constraint of integrality, the answer is no in general. This kind of problems are difficult, and there's no efficient way of solving it. Um, However, throughout the course, we will be paying a special attention to the cases when we still have uh, a way of solving the problem efficiently, and these problems are especially important in industry and applications, and it is vital. It is very important to um, know exactly sorry to know exactly how to distinguish between problems that are hard and the problems that we have no idea how to solve, and the problems which we know how to solve, and you and how to solve them. Okay. So here's an example of an integer program. Um, First of all, we need to note that there are two variables in this problem. These are x1 and x2. Therefore, we can represent the feasible region on a plane. So basically, we're gonna be able to draw things, which is quite important for us to be able to do, especially if we are trying to solve the problem by hand. So we have a linear objective that just sums up x1 and 0.64 x2s. We have a constraint that is saying less than or equal than 250, and we have a constraint that is saying that something is greater than or equal than -4. It is important to mention that before we were talking about the way we introduced um, the linear programming and integer linear programming, we only had the inequalities of the type less than or equal in the first part of the problem. So the inequality of greater than or equal is not very different. Obviously, you can just multiply this entire inequality by -1, you will get minus 3x1 plus 2x2 less than or equal than 4, right? So since it's like now we can just replace this inequality by this inequality, nothing gonna change. So without loss of generality, we can like we don't really care what exactly is the inequality here. At least at this point, we still are calling this problem a linear, like a linear or integer linear programming problem. So our set of constraints are like split into two parts. First is the general inequalities of the form ax less than or equal than b, and the second part of the inequalities are the inequalities of non-negativity. So x1 and x2 must be greater than or equal than 0. The third part of the constraints is telling us that x1 and x2 must be integer. So what are the feasible points at this example? If we draw the feasible set, this is what we're gonna get. So this is the line x1 is greater than or equal than, like x1 is equal to 0. So everything to the right hand side from this line is gonna be inside our set, our feasible set. Everything above the line x2 greater than or equal than 0 is going to be in our set. So this, like everything over here, is also like only sets, only points above this line are going to lie in our set. Then we draw the line, these two lines, 50x1 plus 31x2 less than or equal than 250. And also, so this is 50x1, blah, blah, blah. And so everything below this line must belong to the feasible set. How do I know that it's below? I can just substitute 0 and see that, first of all, 0, does 0 belong to the, like, does 0 satisfy this condition over here? Would anyone answer that question? If I substitute x1 is equal to 0 and x2 is equal to 0. Anyone? So if we substitute x1 is equal to 0 and x2 is equal to 0, we're going to get 0, and 0 is definitely less than or equal than 250. And therefore, this point 0 is, in fact, it actually satisfies this inequality. And by continuity, everything that is in the same half space as 0 will actually satisfy this inequality. So therefore, I know that everything that is below this line will satisfy this inequality. And also, we can draw another line, which is the 3x1 minus 2x2 equal to -4. It's over here. Again, I substitute 0 at this point here, and I ask if it satisfies this inequality. 0 minus 0, it's 0, and 0 is greater than or equal than -4. It does satisfy this inequality, the second inequality, and therefore everything that is below this line will satisfy this inequality from the continuity argument. So our feasible region, if we ignore the integrality constraint, our feasible region is going to be all of the points that are between these 4 lines that I have drawn so far. What if we do not ignore the integrality constraint? Well, in that case, we're gonna be left with these points right here, and only them. So these are all the points that belong to the interior, uh, belong to the feasible set when we did not have the integrality constraint. But they are integral, right? So for example, the point 1, 1 or the point 2, 1, they obviously they first of all they belong to the set that we have drawn, and it also, those points are integral. Therefore, they belong to the feasible set of the original problem that we have right here. So we have found all of the feasible points. If we wanted to solve the problem, what is the way for us to do it? Well, we would need to draw the picture. We would need to draw the first of all. So what is our objective function? Our objective function is x1 plus 0.64 x2, right? What is how does a level set of this function look like? A level set of this function, for example, x1 plus 0.64 x2 equal to 1, it's gonna look something like this. So it's the same as x1 is equal to 1 minus 0.64 x2. So it's going to look something like this, right? And it's going to be much lower. But the point is, all of the level sets of this function, meaning the sets of points with the same value, where the value of the function is the same, are going to be lines that are going to be crossing the plane, and all of these lines are going to be parallel to each other. What we want to do in order to solve this problem, we would like to push this line as far as possible to the right, in this case, so that it still has an intersection with the feasible set. If we are talking about feasible set when we drop the integrality, I would say that, okay, let me actually draw it with a different color, just because we are talking about objective function now. So we are talking about objective function now, and our level sets would look like this, and we are trying to push this line as far as possible to the right, but still make sure that the intersection with the feasible region exists, is not empty. For example, this line right here obviously would not have intersection with the feasible set, just because the feasible set, if we are dropping the integrality constraints, is right here, is this set, and there is no intersection between this shaded region and the blue line I last drew. So that line would not fit our purpose. However, this line right here that passes through this point, this corner point, it would have an intersection with the feasible region, just because this corner point belongs to the feasible region, and it is quite far to the right. It's already pushed to the limit. So the solution of the problem where we have dropped the integrality constraint is going to be this corner point on the top. What if we do not drop the integrality constraint? Well, let me see what happens then. If we do not drop the integrality constraint, we need to push the blue line as far as possible to the right, so that it does pass through one of the black dots inside of this inside of this figure. It looks like to me, at least by just looking at the problem, that this line right here, first of all, it passes quite far to the right, and any line parallel to it that passes through any of these points would be to the left from it. And also, um, it still passes through a feasible point. Therefore, the intersection um, of the level set of the objective function with the feasible region is not empty, and we have pushed the level set as far as possible in order to maximize the level, and therefore we have like the solution of this problem would be this problem would be this point, if I have drawn the level set correctly. If we had a different objective function, for example, if we had the other way around, 0.64 x2 plus x1, and we would like to maximize this, we would probably have a function of this form. We'll probably have a function of this form with level sets parallel to this line, and then we would push it to this point, and this would be the correct solution. Or we could, for example, minimize this thing. We could like if our problem was to minimize x1 plus x2, then our level sets would be of this form, and we would like to push it not as far as possible to the right, but as far as possible to the left. We would be pushing it this way, and this line right here would be the one that still has the intersection with the feasible set, but and pushed as far as possible to the left. So the solution to the minimization problem would be the point 0, 0. So this was the example of a linear integer program that has only two variables and only four constraints. Quite a simple one, and we have solved it for different options with of the form of the objective. I'm wondering if there's any question regarding what I've covered so far. I would expect questions, to be honest. Anyone? Is everything like is there anyone who did not understand literally everything that I have said so far? Is there at least one person in the class? Is everything so clear so that I like there's never going to be anything easier than that? Okay. That's good. That's actually great. Okay, so let's go. Let's continue. And if you think of any question, let me know. So let me get to other kind of examples of problems that we. Okay. So other examples of linear integer linear programming problems are the assignment problem or the integer knapsack problem. The assignment problem is dealing with the problem of assignment, right? Surprise. So we have let's say n people and jobs, and we are trying to assign jobs to people so that one person gets a single job, and each job must be done. And let's say that people like every person has a certain cost of exercising a particular job, and let's say that I know a person who is good in math probably should like probably the cost of doing math for him is lower than a person who's doing, I know, engineering. So basically, we would like to make the cost of executing all jobs as small as possible, while keep doing all of the jobs. The other problem is the knapsack problem, where we have items of different size, different values. Probably some of them are like, I know, like water, then gold, then I know some food, and something, I know, pictures. Um, and we have these items. We have a bag, some bag of like an empty knapsack, essentially, that has a capacity, and we would like to decide which items to carry in the knapsack. I know, for whatever reason we decided to carry it. For example, we are going on an adventure. We would like to maximize the total value of elements in the knapsack. If we're going on an adventure, probably water and food would be of the most of the value. But if we are trying to rob a bank, then probably the golden items would be the most valuable. So we would like to maximize the total value of elements in the knapsack. Both of these problems are examples of integer linear programming problems, and we will be talking in more details about these examples. I just wanted you to have a general understanding of what kind of things could be formulated as linear integer programming problems. A kind of a build up on top of that, on top of integer linear programming problems, are the mixed integer linear programming problems. Essentially, the only difference between the integer and mixed integer is the mixing. Basically, we are allowing some of the variables that we are talking about to be continuous. So x belong to. By the way, I want to explain the notation r plus rn plus is this the set of all vectors x in Rn, so that x are greater than or equal than 0. So we are just dropping this x greater than or equal than 0 by adding this plus. So we are allowing some of the we are allowing our vector to belong to a continuous space, and some other vector we only restricted to have integral values. Our set of constraints is still given to us through a system of linear inequalities, and our objective function is still a linear function. It's just basically you can think about the tuple of vectors x and y as like our previously we had just one variable vector. Now we have a larger vector that consists of two parts, part x and part y, and the part x has n components, and the part y has p components. That is written right here. So and we still have some m inequalities, and our objective function is still an inner product, but instead of having an inner product between c and x, now we have an inner product between the row vector c comma h and the column vector x y. So it's really very, very similar to the linear programming problem. And in fact, if we are talking about the properties, the complexity properties, for example, of mixed integer linear programming problems, they are very similar to the ones of the simple integer programming problems. So we do not get any more complexity out of. Okay, we do get some amount of complexity, but not much more complexity if we allow consideration of continuous variables. So the most of the complexity in the problem comes from the integrality part. So we are talking about the if we are talking about the data now is represented with a lot of different notation. The vector vectors C, H, and B, and the matrices A and G. We're gonna consider them to belong to the space of like their components must be rational. Why it will be like, I will comment on this a little bit later. This is basically a technical reason, but we don't have to stop on about this right now. So the thing is, you can think about this as being drawn from basically some almost continuous set. So like we don't really have any like too much restrictions on the data. But like when we are talking about some technical details, we will be thinking about data belonging to the space of rational numbers. The feasible set for the mixed integer programming problem. So the word linear is actually normally dropped, because if you're talking about mixed integer problems, you normally are talking about linear. So linear is kind of default, and if you're talking about something non-linear, then you add like mixed integer quadratic programs or something like that. So the word linear normally is dropped. The feasible set for this problem can be written in this form. Here I just point out that our vectors x and y are in Rn and Zp, and I also add the system of linear inequalities that is written right here. So basically, this is our capital X that we were talking about before. It's just now denoted with capital S. Nothing too fancy. The pair x and y is is called feasible if x and y belongs to the set S, obviously. X star y star is optimal if Cx star plus Hy star is greater than or equal than Cx plus Hy for any feasible pair x and y. It's just like we have had in the general definition of the optimization problem. Just now we have substituted a specific form of the objective function. Again, I stress your attention that this inequality is participating in the definition talking about maximization problem. The same in the exactly same way I can formulate a minimization problem, and in this case we'll have less than or equal sign right here. A side note about maximization and minimization, I really I think that this must have been covered at some point in the past, but the maximization of an objective function for x in capital X is the same as the negation of the minimization of the negation of the subjective function. What basically is happening here is let's say I have some weird objective function. This is its okay. Let me redraw it. Let's say I have some weird objective function. And this is its maximum, right? And what I'm doing is I'm negating it. So if I'm negating it, negation, I'm getting something like this, right? Where this is the minimum. This maximum corresponds to this minimum. And after I have found this minimum value of the function, I can negate it once again in order to obtain the original maximum value that I was talking about before. So maximization and minimization problems do not differ. Like for each maximization problem, there is a corresponding minimization problem, which is equivalent. You just need to negate everything. In particular, if we are talking the linear about the linear functions, the properties of the objective do not change if you negate it, because the negation of a linear function is still a linear function. If you multiply just because it's a linear function, cx plus hy, if you multiply it by -1, you will get minus cx minus hy, which is still a linear function. So for linear optimization problem, it really doesn't matter if you write down the maximal or the minimum. You just need to make sure that you are careful about all of the signs, that you have done this correctly. The optimal value for the mixed integer programming problem, and optimal values in general, we're gonna be denoting with the letter Z. So if our pair x star y star is optimal for a mixed integer optimization problem, our Z MIP is the value of the objective function at that optimal point. So, and it's called the optimal value. Any questions about the mixed integer linear programs? Okay, so throughout this lecture so far, I started to suspect that some of you might have dysfunctional microphones, because I still haven't heard much. But I really hope that we can fix it throughout the semester. Okay, so yeah, we are talking about the mixed integer linear programs. We are saying that a problem, actually, it's about any optimization problem, but specifically if we are talking about the mixed integer program, it is infeasible if its feasible set S, defined on the previous slide right here, if its feasible set S is empty. We say that a problem is unbounded if for any Z in R, there exists a pair xy that is feasible belonging to S, such that Z is smaller than Cx plus Hy. Let me see. We are actually talking about, yeah. So this is about maximization problem once again. If we are talking about minimization, then this sign must be the other way around. But if we are talking about maximization, how to visualize this for us? We have a real line. This time I will orient it vertically. We pick any number Z on the real line, and for any of these numbers, I can come up with a feasible point xy such that the value of the objective value at this feasible point xy is actually greater than the value of Z. So if Z is here, then I'm able to come up with x and y such that Cx plus Hy is actually bigger than Z. This is what it means to be unbounded. So like for any number, there is a number that is even like there is a feasible point for which the objective function is has an even greater value. If the mixed integer problem is infeasible, then we say that Z MIP is equal to minus infinity. Just just to remember you, Z MIP, if it's feasible, then Z MIP is the value of the objective function at the optimal point, called the optimal value. So the optimal value for an infeasible problem is minus infinity. Again, if we are talking about maximization. If we are talking about minimization, then Z. So let me write it down like this. If minimization, then Z MIP is actually plus infinity. And if MIP is unbounded, then Z MIP is plus infinity for maximization and minus infinity for minimization. So here is the technical detail that I wanted to mention before. So if we say that C, H, A, G, and B all of the data that we are talking about, that we have in our problem, if all of the data is rational, is given with rational numbers, then the feasible MIP either has an optimal solution or isn't unbounded. So as soon as we have at least one feasible point, then we know that there must be a solution, or there's or we can grow the objective function to infinity. The special cases, the very interesting special cases of mixed integer problems are the integer program that we have discussed before. You just assume that p is equal to you just assume that n is equal to 0. Another special case of integer program is the binary program, where you assume that you assume that y is less than or equal than 1. Or in other words, you are saying that y is basically in the set 0, 1. So basically, it can take either 0 or 1 value. The linear program is also a special case of mixed integer linear program, but instead of n being equal to 0, you say that p is equal to 0. So all of these are special cases, and mixed integer linear program is some sort of a generalization of this special cases. Once again, I will repeat that a linear program is the easy special case, while the integer program and the binary program are actually hard special cases. Any questions about mixed integer linear programs?
I had one question.
Wow, that's cool. I'm really excited about this one. Let's go.
If data is irrational, does that lead to the mixed integer problem being too complex? Why are we requiring that the data has to be rational?
Yeah. So if the data is irrational, okay. So this is a quite a complicated matter. Let me see if I can. Okay, I can actually draw that right here. So I will give you an example. So let's think about this way. What are the other options? What's the possibility if we see that a problem, any optimization problem, is feasible? What are the other options except for being having an optimal solution or being unbounded? Can you think of any? This is actually a great question. I just have to say that this is really deep. For example, if we are talking about minimization of x1 plus x2 over a set of x1 greater than 0, x2 greater than 0. Can you solve it? No, there's no optimal solution, because every time you are coming up with a point, I can find a point like closer and closer to 0 that will have an even better value than the one that you came up with. So even though the problem is clearly bounded, right? Like the minimum cannot be less than 0. There's no particular point that would be the optimal point, and this is exactly the thing that is happening to the mixed integer linear programs if you allow the data to be irrational. If the data is irrational, basically what is happening is this is about geometry. You are able to construct a line so that there is an integer point like arbitrarily close to this line, and it keep going. You can construct like a sequence of integer points that is approaching this line and never actually reaching this line. And then if you construct your objective function so that it tries to push the level set as far as possible to this line, you will end up with this kind of situation when you have a sequence of points which are approaching a particular value, a particular objective value, but never reach it. Did this answer your question?
Yeah, thank you.
Awesome.
Yeah,
Great. Thank you very much. Thank you very much. Now I know that I have at least one person with functional microphone. That's great. So let's move on. Any other questions? unless there's any other questions. Okay, so the combinatorial optimization problem. The combinatorial optimization problem is kind of similar to the integer optimization problem, but a slightly different one. So in this case, our feasible set is actually a set of subsets. So our x here is a so our x here is a subset is equal to f. Basically, this f is our capital X, capital X. Our s is the little x. So S is a subset of the set of n elements. This is what's written here. And every subset is being weighted using a function that is linear in terms of the weights of individual elements. So what we are doing here is, let's say that we have like this this is our n and n elements. So this is 1, this is 2, and this is n. And for to each element, I'm assigning a particular value. For this element, I'm assigning value c1. For this element, I'm assigning value c2, and so on, cn. And then I'm choosing a set S. Let's say that this is going to be my set S, and the objective function is going to be defined like as a linear function of the values of this elements, right? So it's going to be like a linear function without loss of generality. You can just say that it's just a summation, just because our C's can be any like anything. So we are just summing up all of the C's from 2 to something, like all of the C's that correspond to the elements that belong to the set S. CJs in this case are called the weights or the values of the elements, and the set of feasible subsets of n is given to us in some form. We are not talking about how exactly this set is given to us, but it is some capital calligraphic F that takes the role of capital X in the very general formulation of the transition problem that we have given. Now the question to you is, how is this related to binary programs? Is there any way to reformulate this combinatorial optimization problem as a binary problem? Oh, anyone wants to speak up?
You just do it as you multiply each CJ by a binary variable about whether or not that particular item J is in the set.
Right, that's exactly the thing. So, but it's very good. So basically, we are summing up over J's that belong to set S, but we don't really have to do that. But let's put it this way: xj is in 0, 1, and we are saying that J belongs to S if and only if xj is equal to 1. If J does not belong to S, then xj is equal to 1 is equal to 0. So basically, this condition here allows us to write down that this actually is the summation over all of the J's. We don't really have to worry about this anymore. And basically, this definition, we don't really have to write it down. It's just our interpretation. Essentially, we just need to write down that we just need to rewrite this set capital F with some set X that is saying that the vector X belongs to the set capital X that has some relation or defined through the F that we have had in the very beginning. Excellent. That's a very, very cool answer. Thank you, Maya. there's a reason why people don't do that, why people have this notion of combinatorial optimization problem, which is mainly concerned with this set f. So if you write it down in this form, there could be a compact form to write down f, the set f. If you write down in this form, chances are that the set x has is a very large set, and there's no way to come to write it down compactly, and most probably the number of constraints that you would need to impose on x is exponential, meaning that it's going to be 2 to the power of n, or like a big O of this thing. So it's going to be a very large number, and people prefer to stick with the combinatorial optimization problem, but there is an option to reformulate as a binary problem. Cool. Now let me kind of now we have this deep dive into the optimization problems, and we already know what is the linear program, we already know what is an integer program, we know what is a mixed integer program, which is a lot. What's the thing that we're going to be doing next? So the course has been designed to teach you 3 different things. First is how to construct integer programs. Given that you have some textual information, let's say you're given a problem. I know your friend came up to you and asked you how to solve this kind of how to find some sort of assignment, or how to find the optimal something, and you should be able to reformulate this in form of a precise mathematical description. This is the thing that we're gonna be doing the first, I would say, the first 3 to 4 weeks. We also be covering what algorithms for their solution exist and how to pick them. So this is more like a theoretical part of the course, which we're gonna be focusing more heavily on in the later part of the course. And the third part of the course is the practical tools, meaning the optimization libraries and practice of coding down the formulations, and asking the solvers, calling the solvers to solve the formulations for you. We will start doing that, I believe, on week 4. I will show you a couple of examples, and starting from there, we will have this kind of problems of solving the integer programming problems with the algorithmic tools in your homeworks as well. So I would say that the first part, where you formulate the problems, and the third part, where you solve them, are the most important parts for the practical for the practical use. It's something that is more like a routine task, and the second part, which is the theoretical part, I would say that it's more like it's a more complicated thing. I really hope that it will deepen your understanding of the subject. So this is what the course is going to be like. So let's start with the first part, with the formulating of the mixed integer programs. Pretty much always, when we want to formulate, when we have the text of the problem and we would like to formulate it mathematically, we most probably gonna start with writing down the necessary variables that we're gonna have in the problem. So you do not have any guarantee that whatever you come up with, whatever variables you come up with, are the exact variables that you will use eventually, but you need to define what appears to be the necessary variables. Then you need to come up with constraints and the objective function. It actually does not matter too much in which sequence you do those, but normally, actually, objective function is something at least slightly more, slightly easier to do. once you have all of the necessary variables. And something that you like, since the constraints are the more tedious part, most probably you're gonna need to introduce new variables in the constraints part. So I would suggest you to start with formulating the constraints, and then as you see that you need more variables, you might have to add some. And then after that, when you're formulating the objective, most probably you already have all of the necessary variables. If you have any complications, define new variables and return to formulating new constraints. It is very important to make sure that you have written down all of the necessary constraints that are important in the problem. There's no like clear way to check that. It's just your kind of understanding of the problem and carefully verifying that all of the real world constraints are actually uh, depicted in your formal representation. Let's consider an example of an LP formulation. So it's linear program, no integer variables required whatsoever. So it's a very simple task. Let's say that we are considering a medical facility that produces different vaccines, vaccine A and vaccine B. 1 millimeter of vaccine A requires 3 units of some compound and 2 units of preservative and 1 unit of compound A. 1 millimeter of vaccine B requires 1 unit blah blah blah, 3 units of something else, and 1 unit of compound B. The facility has 50 units of saline, 40 units of preservative, and 15 units of compound A, and 10 units of compound B. So at this point you should have the clear picture that you have 4 different types of something, and you need out of these 4 types of something, you need to construct 2 types of something. So basically, like, this is at least might give you an idea of how many parameters are there in the problem. So most probably our variables gonna have something to do with the things that we are constructing, and since there are 2 things that we are constructing, you're probably gonna have at least 2 variables. So even without like completing reading the problem, you can already kind of start constructing the problem you had. 1 milliliter of vaccine A can save 6 lives, and 1 milliliter of vaccine B can save 8 lives. The question is, how many milliliters of each vaccine should the facility produce? So it's kind of obvious that our objective function is gonna come in. Is gonna be coming from the sentence before the last one. So we are talking about saving lives, and we know like the information about the number of lives is coming from the sentence before the last one. So most probably the constraints are going to be coming from the first part of the problem, and the objective function is going to be coming from the second part of the problem. So let's see what we can do here. First of all, the variables, as we said. Let's say that X is the amount of vaccine A produced, and Y is the amount of vaccine B produced. Then we know that each item of vaccine A requires you 3 units of saline, and each item of vaccine B requires you 1 unit of saline. So basically, this inequality right here is the inequality on saline. It's telling you that 3 units of the 3 times the number of vaccine A produced plus 1 times the amount of vaccine B produced must be less than or equal than 50, just because 50 is the number of units of saline that we have available. Similarly, we write down the second constraint on the preservative. So we know that vaccine A uses 2 units of preservative, and vaccine B uses 3 units of preservative, and therefore, we're gonna have 2 times X plus 3 times Y. This is the total amount of saline that we are using, given that we are producing X as X items of vaccine A and Y items of vaccine B, and this number gonna be less than or equal than 40, which is the total amount of preservative that we have available. Similarly, we use compound A and compound B, noting that actually vaccine B does not use compound A, therefore there's going to be 0 in our constraint, and vaccine A does not use compound B, therefore there will be 0 in front of X, and thus in the last constraint. And then we know that in advance there cannot be possibly produced a negative amount of vaccines A or B. So there are 2 non-negativity constraints here. This is the canonical form of LP. We can note what exactly are the C, B, and A here. In particular, C here is the vector of C6, 8. B here is the vector 50, 40, 15, 10, and the matrix A here is the matrix 3, 1, 2, 3, 1, 0, 0, 1, right? So this is exactly the form of an LP that we have had before. So you can solve this problem actually, for example, using the graphical method. We can probably practice it during the discussion. So the optimal solution is to make 15 milliliters of vaccine A and 10/3 milliliters of vaccine B, which will save us 160.66 lives. But it's not quite clear to us how many milliliters are there per dose. So, does it make sense to produce a fractional amount of milliliters at all? If we assume that there's 1 milliliter per dose, then this 10/3 does not make any sense, because we're not gonna put 1/3 of vaccine into anyone's. It's not safe. It's a really bad idea. So we assume that so our solution is basically infeasible if we assume that 1 dose is 1 milliliter, because it doesn't make any sense to produce that much. So we need another constraint. We need to add another constraint to our problem, which is the integrality constraint. So here we have found the integer linear programming problem, which is going to be our bread and butter. So we're really happy about this. Now let's switch from the problem with vaccines to the assignment problem. Okay, so let me first see if there are any examples about the vaccines. Any examples? Any questions?
Yeah, I had one question.
Sure.
So we know that vaccine A can save 6 lives with 1 milliliter. So let's say we maybe make the assumption that a dose is 1/6 of a milliliter. How could you represent that in a formulation?
Yeah, that's a good question. So first of all, yeah, I see. So if you have that assumption, then you would need to say that you have, so X is not the amount of milliliters, but X is the amount of units of vaccine. So the number of vaccines A, and the Y is going to be the number of vaccines B, and then you're gonna put here a multiplier, or actually you can even leave it like this. You can just introduce different constraints that are saying that x x over 6 must be in integer, and y over 8 must be an integer. So this is one way to do this. Another way to do this is to introduce this kind of interpretation, and then modify these numbers to account for the fact that now you have more, like now you have, for example, it's going to be x plus y, right? Just because now you need to divide all, like each time you see an x, you need to divide it by 6. Each time you see a y, you need to divide it by 8. So these are two options that you have. Either you add constraints like this instead of x in z and y in z, or you change the interpretation um, of your variables, and then you change the data. You need to adjust the data accordingly. Does that make sense?
Yeah.
Great. I really like the questions. They are very good. I probably need to think more about the way I put weight on the grades, and probably add some additional grades for participation. But I really like the question. Any other questions here?
Yeah, I just had a quick question about the transformation into canonical form.
Right.
Is it just unnecessary to include the x is greater than 0 and y is greater than 0? I noticed they weren't in there.
Sorry, they were not where?
When you changed it into canonical form with your A and your B, they didn't include the constraints x is greater or equal to 0 and y is greater than equal to 0. Is that just like a normal thing, or in the future should we include that in our formulations?
So I have a follow. I have a question to a question.
Yeah.
Are you talking about this slide?
Yeah.
So we do have this inequalities anyways, right? We just, like, I just decided to show you here. By writing this down, I decided to show you the like what exactly are our matrices and vectors from before
Okay.
applied to this particular problem. But this set of inequalities remains in order. So this is just saying to you that max cx ax less than or equal than b, x greater than or equal than 0.
Okay.
This formulation is
Yeah.
right here, so it's not, there's
I
no
just
magic
didn't
here.
remember that x
Yeah,
is greater
yeah,
than 0 was in that
sounds
original
good. Yeah,
formulation.
okay. Any other questions here? Cool. Okay, thank you very much for the questions. All right. So introducing the assignment problem. Everyone loves assignment problem. So you have n special agents available to carry out n missions, or you have n peoples to do n jobs. Some agents are better for certain missions than others. There is a cost Cij if agent I carries out mission J. Your goal is to assign the agents to the missions so that the total cost is minimized. How to formulate this? What are the variables, constraints, objective function? So first of all, like I think we have discussed this, so I will not stop on this any further. Let's jump straight to the formulation itself. So we have n agents and n missions. Cij of agent I is assigned to mission J. So what are the variables in this case? Let's add the interpretation. Let's introduce the variables xi for I from 1 to n. And we say that xi is the mission agent I is assigned to, right? So now, like xi actually belongs from 1 to n. and it is the actual number of the mission. So we have n numbers from 1 to n. What are the constraints? The first constraint is xi must be an integer from 1 to n, which must be a valid mission. It just needs to be an integer from 1 to n, and xi must be not equal to xk for all y not equal to k. So which imposes that one agent per job. By the way, do we need to impose that that each agent takes a job? Do we need that constraint here?
I think so, because if you don't, then the optimal solution would just be to not do any of the jobs, and that would minimize cost.
That's a good point. But we kind of assumed by the interpretation of our variable, we assumed that each agent must take a job, just because for each agent there is an xi. So if we assume that, that's a good point, that it could be the case that we had to impose it if we were to actually. So the thing that I'm doing right now, if you can see it on the slide, this formulation is actually poor. If we were to write down a good formulation, we actually needed a constraint to impose that. But we are writing a poor formulation. For the poor formulation, we don't need that. The objective function is to minimize the sum of all i's from 1 to n. So you will, like, it's not a feasible solution not to assign any jobs to anyone, just because you will always sum all of the, like, you will always sum up and exactly n cij's. The thing is, j in this particular case is given to you with this variable xi. So this is going to be the total cost. Anyone can see.
Oh, quick question. For the objective function or the summation,
Yep.
is it solely just summing over ci sub x sub I, or is it meant to be ci times x sub I? I guess because it's
So
yeah.
So ci comma j is an element of a matrix C. So we have matrix C, and then we have a row that is called I, and we have a column that is called J, and on the intersection there is a number, right? When we are writing down Ci comma xi, that means that we have a row I, and to each I there is an xi that is from 1 to n. So instead of j, we just write down xi, and this is going to be on the intersection of the row I and the column xi. Does that answer your question?
Okay, so I think that makes sense. So that makes sense.
Yeah. So this is not your common way to formulate a problem. I just would like you to analyze this and tell me what is the problem with this formulation. There's clearly a problem with this formulation. What is the problem with this formulation? Why is it bad for the purposes of our class, at least?
It's not linear.
It's not linear, absolutely. Yeah. So we have, for this objective to be linear, we would need ci comma x plus y be equal to ci x plus ci y, just because, like, as we have seen before, the f0 of, we said that a function is linear if f0 of x plus f0 of y is equal to f0 of x plus y, which is clearly not, that does not hold here. So this formulation that we have arrived to, it's not an integer linear program. It is a valid formulation. I just have to say that, like, if you are to solve this problem, you will solve the original problem. It's just not exactly like, it's not exactly about our class at all. So the formulation 2 that we're gonna be doing is better. Again, we have the exact same problem. We have n agents, n missions, the same Cij matrix that we have had before. If agent I is assigned to mission J, we incur cost of Cij. We still need to assign agents to the missions. What are the variables that we would like to use now? The variables that we would like to use now are it is a matrix of variables. Instead of before, we had a vector of variables, and the components of the vector had to be from 1 to n. Now we're gonna have a matrix which gonna have essentially a very similar functionality. Just we're gonna say that in a row I, we're gonna put a vector, a row vector of zeros and ones, and if our xi from the previous formulation was equal to j before, then the j's position on this row I is gonna be equal to 1, and all of the other values in this row are going to be equal to 0. So we fill up this row with zeros, except for a single component of this row. In other words, we can say that xij is equal to 1 if agent I is assigned to mission j, and 0 otherwise. It's just if you think about it, it's just a different decoding of the same thing that we have had before. The constraints here are, first of all, we have to say that our variables must be binary. Xij belongs to 0 or 1. And we have this constraint that agent I does only one job, which is represented with the following constraint, where the summation over j of xij is equal to 1. So it for each j in each column there must be at least one, and actually there must be exactly one. And this time we actually need to impose this constraint that the job J has only one agent, which is basically saying that each agent must hold exactly one job. In every row, there must be exactly one as well. What is the objective function? The objective function is to minimize the scalar product between these two matrices, which is written down with the double sum. You sum over I from 1 to n, you sum over j from 1 to n, and then you multiply Cij with Xij. The cost Cij is going to be included into the total cost if and only if Xij is equal to 1, which is happening only in case we actually take an agent and assign it to mission J. So it looks like we have accounted for all of the necessary constraints, and we have written down the correct objective function. If we decide to write down the full problem explicitly, we would arrive to this formulation. So we have the minimization problem over xij's. We have a linear function here, and we have constraints equal to 1, constraint equal to 1, and then we have an integer or exactly binary constraint in the very end. Here, I want to draw your attention to the fact that we actually have equalities here, which is the first time that we see an equality in our linear programming problem. However, I just have to say that fi of x is equal to some 0, let's say, is actually equivalent to saying that fi of x is less than or equal than 0, and fi of x greater than or equal than 0 simultaneously as a system. So basically, instead of this equation, we could have written 2 inequalities, but who cares? So we're gonna be using equations when we see fit. I want to say that we do not write down linear programming problems or like any like constraints in a particular form, which implies that the same linear program can be written in many forms. So when you for example compare your solution, your formulation to other people's solution, and you see like different inequalities, different constraints, it's like it's kind of okay, just because for the same problem there could be different equivalent formulations. There are systematic ways to like boil down everything to the same formulation. You can try to do this. It's called you can boil down any linear programming formulation to, for example, a symmetric form, or like any form that is of interest to you. You can read about this in the lecture notes for linear programming, like for linear optimization, essentially. Okay, so is this an integer linear program? It is. Moreover, it is a binary problem, just because we have all of our variables belonging to 0 or 1. Any questions regarding the assignment problem or the formulation that we have arrived with? No questions. That's cool. That's awesome. The thing that I would like to cover next is the idea of reformulating max min or min max problems as linear programming problems. So here we are again in the realm of linear programming, and let's say that we have the problem of the following optimization. We have some like set of profits, and we are told that so we can get any of the profits of the 6 profits, for example, with some probability, and we would like to know what is the worst case we're gonna get. What is like if we are really unlucky and we get like the very terrible profit that we can get, how much is it? So in this case, we can write down the okay. So this profits, they depend on some decision variable x. So we say that this profit s1 is like dependent on it depends on x, and this depends on x, and this minimization is over I, where this is basically I. So this is minimization over 6 numbers, but this maximization is over some big set x. So we need to make a decision on this variable x, so that in the worst case we are getting as much as possible. So worst case is represented with this minimum over the 6 numbers, and the maximization is representing our desire to get more profit. Is the problem clear in general? Are there any questions about what exactly we are trying to do? So this this problem can be rewritten in the following way. So let's say that we are again we are maximizing over x, and this thing is actually dependent on x. We can write down the problem of maximization of some dummy variable z. So this is now maximization over x and z. Maximization of z such that z is less than or equal than any of the profits. So for I from 1 to x to 6, we are saying that z is actually less than the any of the profit as I. For visualization, you can think about it as the following. Let's say that we have profits on the following levels. Let's say that for a particular x, our profits are like this. This is S1, or let me put it let me write it down here. This is S1, this is S2, this is S3, this is S4 here, this is S5, and this is S6. S6. So what we are trying to do here, we are trying to say that we are trying to maximize Z, so Z must be less than or equal than any of the profits. So Z must be smaller, like less than this level and this level and this level and this level. So we are basically saying that Z must be less than the smallest of the levels, which is this S6. But these are the available levels for Z. So this Z is possible, this Z is possible, and this Z is possible. Out of all of these possible Z's, we want to pick the largest, which is the largest Z is obviously right here. It's on the same level as 6. So we are matching the lowest bound on Z, which is allowing us to say that we are solving the problem. Formally, if we are to write down math, we can formulate the following statement. Given that we have a function g which is increasing with y, so for any x, if we fix x, we are considering a function g. So let's say that we have fixed x. Our function g of y is gonna have this kind of form. Like it's gonna be strictly increasing. And if we have a problem of maximization of a function g of minimum of some functions, which depend on x, and g itself might also depend on x, this problem right here is equivalent in some sense that I will be talking about right now to the following optimization problem, which is maximize g of zx such that z less than or equal than all of this function that we have had in our formulation. This statement can be proven. I will be doing this, I think, next time. It's not strictly necessary, but I feel like this could be of interest. So during the before the next lecture, you can think about how this two problems can be related. I will just say what exactly I mean by equivalence. When I say equivalent, in this case, I'm saying that the variable x from this problem would be exactly the variable x, the optimal variable x from this problem, and also the optimal value here is gonna be equal to the optimal value of the original problem. So this kind of equivalence is the thing that I'm talking about. Next time we will be talking again about this maximin trick. We will solve an example and continue about talking about other examples of integer and mixed integer programming problems. Are there any questions about what we have covered today? Cool, no questions. So I just want to say that you're very welcome to submit feedback already. You have that in the syllabus. Let me know if you would like the pace to be quicker or slower. I'll see you tomorrow in the morning during the discussion section, where we will be discussing some of the examples. And I will hold office hours still straight after the discussion section, so you are welcome to stop by there as well. Thank you very much for coming to the lecture. Yeah, thanks for your attention. I'll see you next time.